Hi, in this e-lecture, we're going to be looking at the Arduino Uno ADC module. Okay, so we're first going to be looking at some basic concepts regarding sampling and A to D conversion. And from there, we're going to look into how we can configure the ADC module on the AT328P, okay, to fulfill the sampling requirements of the system. All right, so let's get started. All right, so these are the learning objectives, okay, for this module here, where we're going to be first looking at some basic concepts and understand how we can configure the microcontroller registers and how analog device can also be interfaced to the microcontroller to perform the ADC operation. Now, the ADC module, okay, in the AT328P is basically a 10-bit successive approximation A to D converter. The conversion time is given in this range 30 to 260 microseconds. All right, and it has 8 channels. All right, using a multiplexer. So as you can see down here, we have A to D 0 to 7, and it goes through a multiplexer. So at any point of time, one of the signals connected to these channels can be used to perform the conversion. All right, and the conversion configuration and so on, which is what we're going to be looking at right now. Now, though we say that the A to D converter has 8 channels, there are some limitations depending on the type of packaging that we have. Okay, so if you look at the Arduino Uno board that we have in the lab, okay, that is using what we call a DIP package. Okay, DIP stands for dual inline package. So this dual inline package, it has a slightly reduced number of pins. All right, so because of that, you only have A to D channels from 0 to 5. That means you only have 6 channels. Whereas in the other package, which is the TQFP package, you have more pins and you are able to access both the ADC 6 and ADC 7. All right, so there are some Arduino boards that may use the TQFP package, all right, which you may then be able to access those pins. All right, but for the Arduino Uno that we have on the in the studio, all right, the pinout is the packaging is the PDIP package. So the channels that are available are ADC 0 to 5. Okay, so let's look or have a quick overview of A to D conversion. So A to D conversion is basically the concept is when we have an analog signal, okay, like what we have here, we want to perform an analog to digital conversion. We want to digitize the signal. Okay, and to do that, we must basically sample the signal at specific points, okay, at a periodic interval. All right, so in this case, we call that the sampling time. So if I sample it at this point over here, at exactly or one period later, based on the sampling period, I will sample it one more time. Okay, so when I sample the signal, all right, that means I want to capture or take a snapshot of that signal value at that particular time. All right, so that value, all right, will need to be or the value that we assign to that will depend on the quantization levels. All right, so what are quantization levels? So we have a voltage reference, which is the lowest voltage and the highest voltage. All right, and we break it up into a set of levels, or what we call equal steps. All right, and that depends on the number of bits we have for the conversion. All right, so when the ADC module does a sample or takes a sample, it will then allocate it to the level, all right, depending on the way it is configured. All right, so at any point of time, we are going to perform a sample and take the analog or the digital voltage to represent the analog value at that time. So that is this whole process, okay, of converting a analog signal to digital signal is basically done through this concept called sampling, all right, which is what we just discussed. All right, and the rule of sampling which is important to follow is what we call the Nyquist sampling rate, which basically says that we must sample a signal at least twice as fast as the highest frequency component of the signal. All right, so a simple example would be the human voice. So the human voice, the highest frequency is 4 kilohertz. So as long as we sample at 8 kilohertz, you should be able to reconstruct the original signal with close accuracy. Okay, the quantization, as what I mentioned, is basically about breaking up the entire voltage range into a set of equally spaced levels. So that depends on the number of bits we have, all right, in the system. Okay, so the more bits you have, the more quantization levels you have. When you have more quantization levels, the resolution becomes smaller. Okay, the resolution is basically the voltage distance between two adjacent levels. So when the resolution is smaller, it tells us that we can very closely capture the or represent the analog signal using a digital signal. All right, so a simple example would be if I have a 5 volts range and I have only 2 bits to represent this 5 volts, then 5 divided by 2 to the power of 2, which is 5 over 4, which will give me 1.25 volts. All right, so as you can see, the gap between subsequent levels is very high, 1.25 volts. So the error that you will have will be very high. All right, so the more bits you have, the better in representing the analog signal using the digitized value. Now, let's go on to understand the programming procedure, all right, for the microcontroller, the AT328P. So the first step we need to do is we need to activate power to the A to D module. So this is to ensure that the ADC module is powered up. All right, and to do that, we need to write a 0 to the bit 0 of the power reduction register. So that is the first step. The next step is we want to switch on the ADC. Okay, to switch on the ADC, we need to write a 1 to bit 7 of the ADC status control and status register. All right, and the next step is we want to choose the channel that we want to read from. Okay, as we saw just now, the Uno on the that we're using in the studio has 6 channels. So we need to decide which channel we are going to read from. And at the same time, we also need to specify the reference voltage. Once those setup is done correctly, we can start the conversion. Okay, once we start the conversion, we have to wait. All right, so we need to give it some time to complete the conversion. And once that is done, we need to read in the converted value. All right, and this is basically the entire sequence for one sample. Okay, if you want to take continuous samples, you just go to step 4, okay, and start to repeat it again. All right, so now let's go into the details of all these steps that we just saw. So the power reduction register. So the power reduction register is basically used to turn off all the peripheral subsystems power so that we can conserve energy. All right, so to turn on, okay, the ADC module, we need to write a 0, okay, to the bit that corresponds to the peripheral that we want to turn on. Okay, so in this case, we need to execute this code. Okay, so we end, okay, this register with the last bit set to 0, so that will switch on the power to the ADC module. Okay, so now that we have switched on the power to the ADC, we now need to do the next step, which is to switch on the ADC. All right, so this is a 2-step process. So you first switch on or you activate the power. After the power is applied, you need to switch it on again. Okay, I mean, you need to switch on the ADC specifically, and that is done by writing a 1 to bit 7 of the ADC SRA register. Okay, so this is the ADC SRA register, and bit 7 is the AD enable or ADC enable. All right, so once you write a 1 to this particular bit, you are switching on the ADC. Okay, the next step is after you switch on the ADC, we need to set the prescaler. Okay, so the prescaler is basically to determine the clock rate, okay, that is supplied, or the clock that is supplied to the ADC module. All right, so we have the main clock, okay, which is the 16 megahertz clock, and we can pass that 16 megahertz clock through a prescaler. All right, and which prescaler we select depends on the settings over here. So these 3 bits over here, ADPS2 to 0, will determine the prescale clock that we use for the ADC module. Now let's assume this setting. So let's assume we select a prescale value of 128. So the ADC clock will then be 16 megahertz, which is the main clock, divided by 128, which will give us 125 kilohertz. Now this is the ADC clock. All right, that means this is the clock being supplied to the ADC. Now, as we saw earlier, the ADC itself takes some time to perform the conversion. All right, now we can say that a typical conversion takes around 13 clock cycles, though it may take slightly more in certain cases. All right, but typically we can assume it to be 13 clock cycles. So if one conversion takes 13 clock cycles, then the actual sampling rate will be 125 kilohertz divided by 13, which is approximately 9,600 hertz. All right, so that is the again estimated sampling rate, all right, based on the frequency of 16 megahertz and the prescale value of 128. Okay, so now let's look at the entire register as it is. So this ADCS RA register, what we are doing is we are setting the AD enable to 1, and we are setting these 3 bits to 1, 1, and 1. All right, so that is to switch on the ADC as well as the prescale configuration. Now, once we are done with that, we can go on to configure the multiplexing. So this multiplexing is again to select the register, the channel that we want to do the conversion. And this register also has another setting, which is the reference voltage. So that is the bit 7 and bit 6. Okay, so the bit 7 and bit 6 will be used to select the reference voltage for the A to D conversion. Okay, so when any ADC module needs to have a reference voltage, so that you will use that to do its internal conversion. And in the Arduino Uno, the analog VCC is connected to the VCC. So the reference setting, or the reference bit setting, will be 0, 1. Okay, so coming back here, you will take this setting over here to write to bit 7 and bit 6 of this register. In terms of the channel, okay, again, it comes down to the values written in these 3 bits. Okay, and depending on which channel you are going to do the conversion, you just configure the bits accordingly. All right, so in this example code here, we are configuring 0, 1, which is here for the reference voltage, and we are, as an example, going to convert channel 2. So the bits here will be 0, 1, 0 over here. All right. Now, once all of that is done, basically the setup part of the setup for the ADC is complete. Now we can start the conversion. To start the conversion, what we need to do is we need to write a 1 to bit 6 of the ADCS RA register. Okay, so we write a 1 to it. Okay, so if you look at the data sheet, okay, you're going to read how this bit works. Okay, what it tells us is we need to write a 1 to start the conversion, and the bit here will read 1 as long as conversion is in progress. When the conversion is complete, it returns a 0. Okay, returns to 0. All right, so what we are doing is first we write a 1 to it. So this is to start the conversion. And then we want to wait until this bit becomes 0. So this loop here is wait, okay, until it's complete, until ADC is complete. All right, and how this loop works is basically we are taking this register and we're doing an AND with this particular bit. So as long as this bit is still 1, this condition is true. So if this condition is true, I'll be stuck in this while loop. Okay, the moment this bit becomes 0, then this condition becomes false, and then I will go to the next line. All right, so I will basically be sort of stuck in this loop waiting for the conversion to be complete. Okay, so that is what this while loop here does for us. All right, so once the conversion is complete, we can now read the values. Okay, so the values, okay, as we saw earlier, it is a 10-bit A to D converter. All right, and all our registers are 8-bit. Okay, so the answer or the result is actually stored in two registers, ADCH and ADCL. Okay, so what we need to do is we need to sort of pack them together to know the final answer. Okay, so we have a 10-bit answer, and the 10-bit answer is given in two registers. Okay, one is your ADCH, and this is your ADCL. All right, now how do I derive the answer? Okay, or the final answer. So basically what I need to do is I need to make sure that this is rearranged such that the final answer looks like this. Okay, ADCH here and ADCL here. All right, now in terms of the register, again, the actual bits, okay, the default setting is such that the ADCL, you have 8 bits. Okay, so the 8 bits come here. For the ADCH, you have 2 bits, and the 2 bits are over here, the lower 2 bits. All right, so what I need to do is I need to make sure that these 2 bits come here. Okay, 2 bits here plus the 8 bits here. So that will give me the full 10 bits for the answer. All right, so in order for me to do that, what I need to be able to do is I need to shift the answer in the ADCH register to the left by 8. Okay, so when I shift it to the left by 8, all right, so before that I assign it to 2 variables. Okay, and then I shift the answer in the high value to the left by 8. All right, so what happens? Okay, so what will happen is, okay, so let's assume the value in the ADCH is 0, 1. Okay, so the 0, 1 will be here, and I move this to the left by 8. So from 0, 1, when I move it to the left by 8, it will come to bit position 8 and 9. All right, and when I do an addition, okay, so this will be the high value shifted left by 8. And I when add to the ADCL, okay, or the low value, all right. Okay, so in this case, I will read from the low value, and what will happen is the low value as the answers are in the bit position 7 to 0. Okay, so this will give me the final answer, which is the full 10 bits from 0 to 9. Okay, so that is what is happening over here. Okay, when I do the reading of the values. All right. Okay, in terms of the pin mapping, all right, the mapping of the analog signals are shown here. So ADC 0 to 5 mapped to the A0 pin 1, A0 to A5 on the Arduino pinout connectors. All right, so on the board itself, you can actually see the labels there, A0 to A5 as analog input pins. Okay, so ADC channel 0 maps to analog input 0 and so on. Okay, so let's see it in action in the lab. Okay, so in the lab, basically what you're going to be using is you're going to be using a flex sensor. Okay, and the flex sensor is basically a sensor where as you flex it, okay, you can actually you're actually changing the resistance. All right, and that resistance, as you change it, you can capture it using the A to D converter. All right, so it's connected to A0 over here. Okay, so analog channel 0. All right, and this is the hardware connection, okay, that we need to use, and we are also driving a LED to sort of control it to reflect the bending of the flex sensor. So this is the code. All right, so let me just run through the code with you. So in this first line, we are basically turning on the power for the ADC module by making sure that the ADC bit is cleared to 0. Okay, and this second line, the ADCS RA, we are performing the following configuration. First, we enable the A to D module. We set the prescaler to 1 to 8. All right, so that's what we are doing here. Next, in this next line, we are selecting the channel. So in this case, we are selecting channel 0 because that is how the circuit is shown in the studio handout. All right, and then finally, we are setting this port B pin 5 as output. So this port B pin 5 output is for the LED control. Okay, in terms of the loop, okay, what we are doing is we are continuously performing the A to D conversion. So first we start the conversion by writing a 1 to the A to D start conversion bit. Okay, once that is done, okay, we go to we come to this line where we are waiting in this line as long as the ADC-SC bit is 1. The moment the ADSC bit is cleared to 0, then the conversion is complete. Then I come to this line over here. Okay, so in this line, okay, we are reading the values. Okay, so let me just go back here to highlight this. I think the typo here, this should be low value. Okay, because you already read the low value from the ADCL register, so this should be low value, not ADCL. All right, so that is correctly shown here in the code. All right, so when I reach this point here, I already have the ADC value, okay, of based on the how much I bent the flex sensor. All right, and what I'm doing here is I am toggling the LED connected to port B pin 5, and then I do a delay. So the amount of delay is basically based on the amount of the result I get from the ADC conversion. Okay, so if the ADC result is low, then I delay very little. If the ADC result is high, I delay longer. Okay, so when you run this code, you should be able to see that as you are flexing the sensor, all right, the resistance changes, so the ADC value changes, and as a result, the rate at which the LED blinks also changes. Okay, so that is basically what you first do, all right, and after you do it in the polling approach. So why is this polling considered polling approach? Because of this. Okay, so we are polling to while we are waiting for the SC bit to go from 1 to 0 to indicate that it's complete. So it's the polling mode. All right, then in the next part of the studio, you will be next activity in the studio, you'll be looking at the interrupt approach to achieve a similar outcome, and then we will sort of compare and see how different the interrupt approach works compared to the polling approach. All right, so yeah, so that brings us to the end of this e-lecture. Okay, so I hope you have fun in the studio with the ADC module and the flex sensor. All right, thank you. Bye.